The edge of our solar system is on fire, and nobody can explain why. Temperatures out there in the darkest, most remote region of space are hotter than the surface of the sun. Physics says that's impossible. And yet, it's real. By the end of this video, you'll understand exactly what that boundary is, why it breaks the known laws of thermodynamics, and what it would take to build a ship capable of punching through it alive. This is the most hostile engineering problem in the history of human spaceflight. Let's start with the thing physicists call the heliopause. Think of our sun as a giant engine constantly exhaling. Every second, it fires off a stream of charged particles called the solar wind, blasting outward in every direction at over 400 kilometers per second. That wind doesn't stop at Earth. It doesn't stop at Mars, or Jupiter, or even Neptune. It travels for billions of kilometers, until it finally hits something. That something is the interstellar medium, the thin, cold gas and dust that fills the space between star systems. When the solar wind collides with that boundary, it slows down, piles up, and forms a giant invisible bubble around our entire solar system. That bubble is called the heliosphere. And its outermost edge, where the sun's influence finally ends, is the heliopause. Voyager 1 crossed it in 2012. It was the first human-made object to leave the heliosphere, ever. Scientists cheered. And then the data came back, and something was deeply, fundamentally wrong. The temperature on the other side of that boundary wasn't dropping. It was rising. Dramatically. Interstellar space, which should be brutally, lethally cold, registered plasma temperatures of nearly 30,000 to 50,000 Kelvin. For context, the visible surface of the sun runs at about 5,500 Kelvin. The region beyond our solar system was hotter. By an order of magnitude. Physics has a rule. A simple, iron rule. The further you get from a heat source, the colder things get. Energy dissipates. Entropy increases. Heat flows away from hot things, not toward cold ones. The heliopause violates that rule in plain sight. So what's actually happening out there? Scientists have a few competing theories, and none of them are fully settled. But here's the most compelling one. The interstellar medium isn't empty. It's laced with magnetic fields, cosmic rays, and a particular kind of radiation born from supernova explosions thousands of light-years away. When these high-energy particles slam into the heliopause boundary, they don't just pass through. They interact. They compress. They generate electromagnetic turbulence at a scale that dwarfs anything we can recreate on Earth. Think of it like this. Take a cold river and a warm ocean. Where they meet at the estuary, the mixing creates turbulence, unexpected waves, eddies, sudden temperature spikes. Now scale that up by a factor of 1 trillion, and replace the water with charged plasma and magnetic field lines moving at relativistic speeds. The energy released at that collision zone is staggering. And it manifests as heat. But here's what they didn't tell you in the news coverage. Voyager's instruments weren't even designed to measure this properly. The probe was built in the 1970s. Its plasma sensors failed years before it crossed the heliopause. What we know about the temperature out there is being inferred from incomplete data, from a 50-year-old spacecraft running on 22 watts of power, less than a refrigerator light bulb. We are extrapolating the most extreme environment in our solar neighborhood from instruments that were obsolete before the internet existed. Which means the actual temperatures could be even higher. And that brings us to the real problem. Because there's a mission on the drawing board right now, an actual, funded concept to send a purpose-built probe beyond the heliopause. To go there deliberately. To study this boundary up close. But to do that, you need to build something that can survive it. And before we talk about how you'd build that ship, you need to understand something even stranger about what it would have to cross. The heliopause isn't just hot. It's a radiation kill zone. Inside our heliosphere, the Sun's magnetic field acts like a planetary shield, deflecting up to 75% of the galactic cosmic rays trying to pour in from deep space. The moment you cross the heliopause, that shield disappears completely. You are now exposed to the full, unfiltered fury of the galaxy. Galactic cosmic rays are not like the radiation from a nuclear reactor or even a solar flare. They are protons and atomic nuclei accelerated to near the speed of light by supernovae, black hole jets, and magnetar explosions across the Milky Way. They carry energies millions of times higher than anything a particle accelerator on Earth produces. They punch straight through aluminum, through titanium, through standard radiation shielding like it isn't there. For a human crew, unshielded exposure beyond the heliopause would be lethal within days. But even for electronics, for the silicon chips, memory systems, and processors that guide a spacecraft, cosmic ray bombardment causes what engineers call single-event upsets. Bit flips. Random errors embedded into the computer's logic with no warning. Enough of them, and your ship goes dark. Permanently. And here's the scale problem. The heliopause sits roughly 120 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. You're talking 18 billion kilometers from home. A radio signal traveling at the speed of light takes over 16 hours to reach you one way. If something goes wrong out there, no one is coming. No one can even answer your distress call for an entire day. So how do you build something that survives all of that? And here's the shocking part, the answer might already exist. In concept, at least. The mission is called the Interstellar Probe. It's being seriously evaluated by NASA right now. The goal, reach 1,000 astronomical units, nearly 10 times beyond the heliopause, within 50 years of launch. To do that, the spacecraft would need to travel at roughly 20 astronomical units per year. For reference, Voyager 1, the fastest object humanity has ever launched, manages about 3.6. The only propulsion system capable of hitting those numbers is a solar obverse maneuver, a terrifying, elegant trick where you dive a spacecraft toward the Sun, skim just above its corona at extreme speed, and then fire your engines at the moment of closest approach. The Sun's gravity acts as a slingshot, catapulting the probe outward at unprecedented velocity. You'd need a heat shield capable of surviving 2,500 degrees Celsius on the sunward side, likely made from carbon-carbon composite foam, the same material tested on the Parker Solar Probe. Then comes the radiation hardening. Engineers are designing processors built from silicon carbide rather than standard silicon, a material that maintains function at extreme temperatures and resists cosmic ray bit flips. The spacecraft's core computer would be triple redundant, with a voting system. 3 processors run simultaneously, and if one produces a different answer, it gets outvoted. The ship corrects itself automatically. And the power source? Nuclear. Specifically, a next-generation radioisotope thermoelectric generator using plutonium-238. No solar panels work at 120 AU. Sunlight out there is 14,000 times weaker than at Earth. The nuclear core keeps the instruments alive, keeps the heater running, keeps the data flowing across those 16-hour signal delays, for decades. This isn't science fiction. The materials exist. The physics works. The only thing missing is the decision to build it. Here's the thing. This mission isn't just about exploring our backyard. The heliopause is the last piece of territory our civilization has any claim to understand. Beyond it lies interstellar space, the ocean between the stars. The same ocean any future civilization would have to cross to reach another sun. Understanding the radiation environment, the magnetic topology, the temperature anomalies at that boundary, that's not abstract science. That's the prerequisite knowledge for every interstellar mission that comes after. You cannot navigate a sea you've never mapped. And right now, the only maps we have were drawn by 2 spacecraft launched during the Nixon administration, using instruments that were never supposed to last this long. We are overdue for a better look. The edge of our solar system is burning with energy we don't fully understand, wrapped in radiation that could kill anything we send through it, and we're building the thing that goes anyway. That's the most human sentence I know how to write. If this broke your brain a little, subscribe. We drop one of these every week. Next week, the object at the center of our galaxy just sent out a flare so powerful it lit up the far side of the Milky Way, and astronomers caught it in real time.